Try this before you read on. Take a single sheet of paper from your textbook and try to measure its thickness with a millimeter ruler. Look closely at the scale. The smallest gap between lines is 1 millimeter, and a single page is far thinner than that. You literally cannot read a value for it directly. You've already used two of the simplest measuring tools in physics, a ruler and a measuring cylinder. A ruler gives you length directly, in millimeters or centimeters, just by reading the scale where an object ends. A measuring cylinder works the same way for volume, giving a reading straight off its scale, in cubic centimeters or milliliters. Picture a pencil laid along a ruler. Line the ruler's 0 mark up exactly with one end. Then look straight down at where the other end meets the scale. A tilted eye line or a gap at the 0 mark throws off the reading before you've even started. Now picture water in a measuring cylinder. Its surface curves slightly where it meets the glass, a meniscus. Bring your eye level with the liquid and read the mark level with the bottom of that curve. Read from above or below, and the value shifts, even though the water hasn't changed. Here's the problem hiding behind that ruler reading. A ruler's smallest division is 1 millimeter, so any single reading carries an uncertainty of roughly that size. If the object itself is only a fraction of a millimeter thick, that uncertainty is bigger than the quantity you're trying to find. You need a technique that shrinks the error relative to the measurement. So instead of measuring one page, measure many. Press 50 identical pages tightly together and measure the stack. Say it comes to 5.0 millimeters. Divide by the number of pages. 5.0 millimeters divided by 50, giving 0.10 millimeters per page. The ruler's 1 millimeter uncertainty is now spread across 50 pages instead of sitting entirely on one. Time intervals need the same care. A standard clock usually marks divisions of 1 second, fine for timing minutes. But a digital stopwatch typically reads to 1/100th of a second, giving far finer resolution when an event happens quickly. Suppose you time one swing of a pendulum with a stopwatch reading to 0.01 seconds. Is that single reading trustworthy? Think about the moment your thumb presses the button to start and stop it. Your own reaction time adds error into that one measurement. And for a fast swing, that delay can be a large chunk of the total. The fix mirrors the paper stack. Time 20 complete oscillations in a row before stopping the clock. If that takes 30.0 seconds, divide by 20 to get a period of 1.5 seconds per swing. Your reaction time error still happens twice, at start and stop, but now it's shared across 20 cycles instead of one. So, why does dividing by 20 actually help? The fixed error from your reaction time stays the same size, no matter how long you time for. Spread that same fixed error over 20 oscillations instead of one, and the error in each individual period shrinks to a small fraction of a second. Now, a different kind of question. Two cars each travel at 60 kilometers per hour, one heading north, the other south on the same road. Are these the same situation? The speed value alone tells you nothing about which car is going where, and that missing piece, direction, turns out to matter enormously. This is the difference between a scalar and a vector quantity. A scalar is completely described by a number and a unit. Nothing else is needed. A vector needs that same number and unit plus a stated direction before the description is complete. Leave the direction off a vector quantity, and you've only given part of the answer. Distance, speed, time, mass, energy, and temperature are all scalars. Ask yourself why. Does it make sense to say a mass has a direction, or that a temperature points north? It doesn't. These quantities are fully pinned down by size alone, so direction simply has no physical meaning for them. Force, weight, velocity, acceleration, momentum, electric field strength, and gravitational field strength are vectors. Each one changes its physical effect depending on which way it points. A force pushing left does something completely different from the same-sized force pushing right, even though both have identical magnitude. Here's a mix-up worth catching early. Are speed and velocity just two names for the same thing? Not quite. A car going round a bend at a steady 30 kilometers per hour has constant speed, but its direction keeps changing, so its velocity is changing too, even though the speedometer never moves. Speed gives magnitude alone. Velocity adds a direction. On a vector diagram, an arrow does two jobs. Its length, drawn to scale, represents magnitude. A longer arrow means a bigger force or faster velocity. Its orientation represents the direction that quantity acts in. When two vectors act at right angles, draw them as two arrows meeting at a corner, ready to be combined. To combine two right-angled vectors into one resultant, you need two things. The magnitude comes from Pythagoras' theorem. Square each vector, add those squares, then take the square root of the total. The direction comes from the tangent ratio. The angle equals the inverse tangent of one vector's size divided by the others, measured from whichever vector you choose as your reference. Try it with a 3 Newton force pulling east and a 4 Newton force pulling north on the same object. Square each one, 9 and 16, add to get 25, then take the square root. 5 newtons is the resultant. The inverse tangent of 4 divided by 3 gives about 53 degrees from the 3 Newton force. Now, apply that method yourself. A swimmer moves straight across a river at 2 meters per second, while the current pushes them along the bank at 1.5 meters per second, at right angles to their swimming direction. What's their resultant velocity? Squaring and adding gives 4 plus 2.25, or 6.25. The square root is 2.5 meters per second. And the inverse tangent of 1.5 over 2 gives the angle off their swimming line. Quick check. Is momentum a scalar or a vector, and why? Momentum depends on an object's velocity, and velocity itself carries a direction. Because reversing that direction changes the physical momentum, think of a ball bouncing back off a wall. Momentum must be classified as a vector, not a scalar. Bring these ideas together, and you've built 2 habits that support almost every calculation ahead. Measuring multiples, a stack of pages, 20 oscillations of a pendulum, turns an unreliable single reading into a dependable average. Sorting a quantity as scalar or vector, then combining right-angled vectors with Pythagoras and the tangent ratio tells you exactly what information a calculation needs. Next time you meet a new quantity, ask, how would I measure this accurately? And does it need a direction to be complete?